You're watching the 4.3 lesson video on exponential models and percents. We're going to jump right into this lesson because this is a continuation. So we are still talking about exponential functions. We're now just going to take a look at how percentages can play a major role in exponential functions. And I know what some of you are thinking right now. Oh, great, here we go with decimals again. I hate this stuff. But what I will tell you is that this topic is something that continues throughout all of the Common Core algebra related courses, and I actually have this conversation with my SAT students who are juniors all the time. So if this is something that you can master as a freshman, you are going to be in very good shape over the next few years, especially for those of you who are planning on taking the SAT exam. So exercise number 1 tells us to write each statement as a single positive percent and then as a decimal. Well, one thing to keep in mind is that we can either have percent growth or decay, or increase or decrease. But the main thing that we need to do, and I'm actually going to write this up top, is we are always going to compare to one whole, which is actually 100%. And I couldn't put enough exclamation marks on this if I tried. So this is huge. Highlight it. Put balloons around it. I don't care, but you need to know it. Okay, well, what do I mean by this? A percent growth of 8%. Well, if I'm increasing something by 8%, what am I starting with? Well, I'm starting with one whole, or really 100%, and we're adding 8% onto that, which is 108%. Now, as a decimal, taking percents and writing them as decimals means per 100, which means we're just taking the decimal place and we're dividing by 100, which moves the decimal place 2 spaces to the left. So 108% is really 1.08. And the reason why we're doing this is because in math problems, we cannot use percents. We always have to write them as decimals. All right, B says a percent decay or a percent decrease of 9%. So we start with 100%, we take away 9%, and what are we left with? Well, we now have 91%, which as a decimal, move that decimal place 2 spaces over, this is really the same thing as 91 hundredths per 100, 91 hundredths. C, an increase, so we're adding 5.5% onto 100. I guess I should have written that percent symbol. Let's put it on here. So this will become 105.5%. And some of you might start panicking. Oh my goodness, there's a decimal in a percent. Is this possible? Do we have to change it? We sure do. Relax, it's okay. Move the decimal place, same thing. We just move it 2 spaces over to the left. So we get 1.055 as the decimal. No big deal. All right, a decrease, so we are taking away 20%, again, from our 100, and we end up with 80%. Moving the decimal 2 spaces over, this would be 0.80 or just plain old 0.8. Potato, potato means the same thing to me. We're going to use this concept of comparing to 100 throughout the rest of the time that we talk about exponential growth and decay when we deal with percent growth and percent decrease. All right, exercise 2 says a population of fruit flies is growing at a constant rate of 20% per hour. The initial population, so the starting population before anything happens every hour, is 28 flies. Let's put that right in the table. Now, oftentimes on a Regents exam, they are not going to give you the table. You will have to come up with the table of values. But I'm hoping that by the time we're done with this unit, you're going to realize how important the table of value is, and you're just going to naturally come up with the table of value, or table of values, I should say. And this is something that is consistent for linear functions, exponential functions, our next type of functions, which is called quadratic. Looking at the table can tell us so much information, and we can make so many connections. So table, table, table. All right, move on. Part A, write growing by 20% as a single positive percent. Okay, on your own, go. Did you end up with 120%? Because that's what you should have. Nice job if you did. B says write a formula using before, now, next rules and state the initial value. Well, we know that the initial value, so P of 0, is how many flies? 28 flies. And how will we get to the next? So in order to get to the next term, we're going to look at the now, and we're going to multiply that by, well, I can't multiply it by 120%. Let's write it as a decimal. 1.20. Because this would show us, instead of having to just multiply it by 20% and then add it on at the end, which maybe is something that you were used to doing, we want to take care of this increase by 20% all in one step. Now C says complete the table above, and it says to round each value to the nearest whole number because we don't want parts of fruit flies. I mean, fruit flies are small enough as it is. Let's not count their wings. Okay, let's go ahead. Let's do C. I'm going to open up a new document, and let's add a calculator. So I start with 28, and I'm going to multiply that times 1.2. I end up with 33.6, but it says to round. Let's put in 34. Next, 34 times 1.2 or 1.20, same thing. Rounding, we would get 41. And the nearest whole number just means get rid of decimals. For those of you who were confused about that, I should have clarified. So 41 times, you got it, we're increasing by 20% again. 49 fruit flies. Go ahead, finish off the rest of the table, and I'll do the same. So here we are looking at the completed table of values. One thing to keep in mind is that we rounded in our table. So if we come up with a rule, our numbers will be slightly off from what the calculator calculates because of the fact that we were calculating our numbers and rounding as we went every single time. All right, so moving on to, where are we? Part C, we have to look at D. Let's graph all of these points. I'm going to pause the video because I think that you can do this without my assistance. Now, when you first started graphing this, it appeared to be linear, but if you put a ruler on it, which is absolutely something that all of us should know to do right now if we think it's a linear function, you would see that these points would not make a straight line. Instead, there is a slight curve, which ends up happening to look something like this. Now, it says based on this should actually say part B, we need to come up with a function that models this population. All right, so because of this, we know how to kind of write out these rules. We start with our output, and we say, how do we get our output? Well, in order to get our output, we have initial value. In this case, we had 28 flies, and every single time, what were we doing? Well, in our calculator, we were multiplying by 1.2 over and over and over and over and over again, the number of hours that have gone by, to the t power. Let's add a page, graph it, and I want to look at its table. So 28 times 1.2 to the, not t power, remember we have to use x, to the x power. We don't really see much going on in our graph. In fact, we don't even see anything in the first quadrant because of the window, which maybe it's a good idea to go ahead and change to something closer to what we have going on over here. The 10 looks good. It looks like we have a minus 10. That's fine. And over here, we are not really looking at much else. And as you can see, it is a nice slight curve. It's not growing at a very fast rate because we're only multiplying by 1.2 every single time. Where in some of the models beforehand, in our other lessons, we were looking at times 3 or times 4 or bigger numbers. All right. F says use your function, determine how many flies there will be after 1 day. Well, how many hours are in 1 day? That would be 24. So if I hit Control T, I'm going to notice, and I'm just going to scroll up here for a minute, I'm going to notice that 028 is there, but my numbers, remember what I was talking about earlier? The numbers are slightly off, but that was because we were rounding. They're very close. So typically, if we were to come up with an exercise like this and it didn't tell us to do any rounding, we would be writing all of these actual values in the table of values here. But right now, we're just kind of dabbling with the fact that we're dealing with percentages, so we're going to follow directions in maybe different ways depending on what the problem is telling us to do in terms of the rounding. So here, we're using our function. We're using the p of t equals 28 times 1.2 to the t, but in this case, we're putting in 24. Now, I could go back on my calculate page and figure out what this piece here would simplify to, but instead, let's use our awesome table of values because it will give us the same exact thing because we typed in the exact value or the exact values into our function. So after 24 hours, it appears to be, you know what, this question is a little, it hasn't been written correctly because we should talk about some type of rounding, but here I am going to round, so 2, 2, 2, and let's round to the nearest fly, so that would be 2226. So 2,226 flies. And here it says state the range of the population. So how low does it go? So how low does it go from 0 all the way, and this is p, so from 0 of our t value all the way to 24. Well, we know our output at 0 is 28. And our output at 24 we just found above there is 2,226. So the range would be from 28 flies all the way up to 2,226 flies. And both of those numbers are included. So what we are going to do is close off with brackets. Moving on to exercise 3, it says, as water drains out of the pool, the depth of the water decreases at a constant rate of 28% per hour. The depth of the water when the draining begins, so dun dun dun, here's our initial value, is 40 feet deep. It says when the time is equal to 0, that didn't copy very well, hopefully it looks better on your papers. How deep is the water? Well, they're just asking you the initial value, or the starting point of 40 feet, and we know by now that this is the y-intercept. So this would be represented by 0, 40. We could even plot this right on our graph here if we wanted to. Let's draw an arrow. Okay, B says write decreasing at 28% as a single positive percent. What do we compare to? You guessed it, 100% minus a 28%. So 100% minus 28% would be 72%. And just because we should know by now where this is going, somewhere in the problem, let's convert it to a decimal, so 0.72. C says based on the two parts above, let's come up with an equation that will give us D. So D of time, so we're going to put in time, it's going to predict the depth. So we start at 40, our y-intercept, and we will have to multiply repeatedly by 72% because we're losing that 28% every single hour. All right, now we can go back to our calculator. Actually, I'm just going to add a new page since we're working in the same lesson. and we're going to type in 40 times 0.72 to the, in this case, x power. Hit enter, and it looks like we need to complete the table of values, and here it says round each value that we see in the table to the nearest foot, which is slightly different from what we did before, but let's follow directions. So 0, 40, 1 would be 29, 2 would be 21. Take a minute and fill in the rest of this table on your own. Please check your table of values with mine and pause the video and go ahead and graph. I'll do the same. I'm hoping that your graph and my graph look the same. Notice how we start at 40 and we get closer and closer to the depth being 0, but it will never actually touch the x-axis, and we know the reason why because we've talked about this many times before. So E says it's safe to cover the pool after it reaches a depth of less than 1 foot. So what is the minimum number of whole hours that we should wait to cover the pool? Well, let's look at our table of values. If I keep scrolling down, we can see that after 11 hours, it's 1.07 feet deep. After 12 hours, we now have reached below 1 foot. So after 11 hours, we still have a little over a foot of water, but after 12 hours, so this is what we would use here, 12 hours, the table is below 1 foot. In this case, 0.77633, and so on and so forth. Moving on to exercise 4, it says which of the following equations would model an exponential quantity that begins, so here's our y-intercept, we start at 16, and decreases at a rate of 8%. Well, let's take away 8% from 100, we end up getting 92%, which is the equivalent of 0.92. So this is a number that we're looking at. This is our multiplier because we're multiplying per means multiply, per hour. 4 doesn't make sense. 2 doesn't make any sense because we're adding the 16, or actually we're adding the 0.92. We are multiplying 16 by 0.92 every single time. 3 was a trap. It looks like we were adding 8%. 3 would have been good if they asked us if the quantity was increasing at a constant rate. Okay, exercise number 5 says if $350 is placed in a savings account that earns 3.5% interest every year, then how much would the savings account be worth after 10 years? Well, right away, compare to 100. So 100 plus 3.5 is 103.5, and don't forget that label of percent, because now we know we're going to take our decimal point and move it 2 spaces to the left to write it as a decimal. So this is 1.035 as our multiplier. So to get our output, maybe we'll say, it doesn't really tell us anything here, so our output will equal the initial amount of money, so 350 times the multiplier over and over and over again, but in this case, they told us after 10 years. So in our calculator, let's just use our function. We just need to simplify the right-hand side. 350 times 1.035 raised to the 10th power, which would equal, if we look at our answer choices, that ends up becoming $493.71. Notice how they rounded to the nearest cent, because that's how money works. All right, we're almost there. Exercise number 3, a colony of ants has a population of 5.4 million. It is decreasing at a rate of 2%. Okay, you know the drill. 100 minus 2% is 98%, which is 0.98 as a decimal. We first need to write 5.4 million in scientific notation. Oh my goodness, this is bringing back the memories. So 5.4 million would be 5.4. What is 5.4 million anyways? Maybe this will help us to see. So if we write this as 5.4 million, we'll have 5, 4, followed by 2 more zeros, and then, of course, 3 more zeros. So this is 5,400,000. If I write this as scientific notation, we can see that our decimal place was moved 1, 2, 3, 4, 5, 6 spaces to the right. So 5.4 times 10 to the 6th. Then it says to write a function that can be used to find the population, p. So we can write p of, in this case, days. We'll put in our days. We started with 5.4 times 10 to the 6 ants. That represents 5.4 million. And that's our starting value. It looks a little weird, and I had to use parentheses, but our multiplier here is this 0.98 every single day. So to the d power.